2024, scientists pointed the most powerful telescope ever built toward the edge of the observable universe, and what they found made some of them wish they had never looked. Galaxies that should not exist, black holes that defy every known law of physics, a mysterious new class of objects that no one had ever predicted. And perhaps most terrifying of all, evidence that the very force holding our universe together, the force driving its expansion, the force that determines whether everything ends in ice or fire, that force appears to be dying. This is not science fiction. This is not speculation. This is what the James Webb Space Telescope has actually observed, confirmed by multiple independent teams of scientists across the world, published in the most prestigious journals in physics, and debated in emergency sessions at astronomical conferences from Washington to Geneva. And by the time you finish watching this video, you will understand why some of the most brilliant minds in astrophysics are calling this the biggest crisis in the history of cosmology. You will understand why textbooks written just 5 years ago are already obsolete. And you will confront a question that even the scientists themselves cannot yet answer. Is our universe heading toward an eternal frozen silence, a violent collapse back into nothingness, or something so catastrophic that even the atoms in your body would be ripped apart? Everything you thought you knew about the universe is about to change. And it all starts with a single telescope, floating 1 million miles from Earth, staring into the darkness of deep space and finding things that were never supposed to be there. Welcome to a journey that will take us from the birth of the cosmos to its possible death, from the first photons of light that ever existed to the last stars that will ever shine. Today we are going to explore every single discovery that the James Webb Space Telescope has made that has shaken the foundations of modern astronomy. We are going to go deep. We are going to go detailed. We are going to explore every angle, every implication, every terrifying possibility. Because this is not just a story about a telescope. This is a story about who we are, where we came from, and where everything, absolutely everything, is headed. Let me tell you what we are going to cover today, because this is going to be unlike any video you have ever watched about space. First, we are going to talk about the impossible galaxies, massive, fully formed galaxies that appeared in the universe so early that no model of physics can explain how they got there. Then, we are going to dive into the supermassive black holes that James Webb found lurking in the early universe. Black holes so enormous that they should have taken billions of years to grow, yet there they were, fully formed, barely a few 100 million years after the Big Bang. After that, we are going to explore the most mysterious objects James Webb has ever discovered. Tiny red dots scattered across the ancient universe. Objects so strange that for years scientists could not even agree on what they were. And just weeks ago, in June of 2026, a team at the University of Texas finally cracked the code. And what they found inside those little red dots is genuinely mind-bending. Then, we are going to confront the Hubble tension, the crisis that has torn the astronomical community in two, because the universe appears to be expanding at two completely different speeds, depending on how you measure it, and James Webb was supposed to fix this problem, but instead made it dramatically worse. From there we will enter the darkest chapter of all, literally, because new data from the largest three-dimensional map of the universe ever created suggests that dark energy, the invisible force that makes up 68% of everything that exists, is weakening. It is losing power. And if that is true, then the ultimate fate of the universe, the question of how everything ends, has just been completely rewritten. Finally, we will pull all of these threads together and confront the biggest question of all. Is the standard model of cosmology, the framework we have used for 3 decades to understand the universe, is it broken? And if it is, what comes next? These are not disconnected discoveries. They are pieces of a single terrifying puzzle. And the picture that puzzle reveals, when you step back and look at it all together, is something that even the most seasoned astronomers were not prepared for. So if you are the kind of person who looks up at the night sky and wonders what is really out there, if you are the kind of person who wants to understand not just the headlines but the deep science behind them, then you are exactly where you need to be. Hit subscribe right now and tap that bell icon so you never miss a deep dive like this one. And I want you to do something for me. Right now, before we go any further, drop a comment and tell me, do you think the Big Bang model is broken? I read every single comment, and I want to know what you think before we get into the evidence, because by the end of this video, your answer might be very different from what it is right now. Let us begin. To understand why what James Webb found is so shocking, you first need to understand why this telescope exists in the first place. Because the James Webb Space Telescope was not built on a whim. It was not some routine upgrade. It was the single most ambitious, most expensive, most technically complex scientific instrument that human beings have ever constructed. And it was built for one very specific purpose: to see what no telescope had ever seen before. The very first light in the universe. Let me take you back. For decades, our window into the distant cosmos was the Hubble Space Telescope. Hubble was revolutionary. Launched in 1990, it orbited the Earth at about 540 kilometers above the surface, and it gave us images of the universe that were so stunning, so detailed, that they fundamentally changed how humanity sees its place in the cosmos. Hubble showed us that the universe is not a static, unchanging place, but a dynamic, violent, breathtakingly beautiful arena where galaxies collide. Stars are born and die in spectacular explosions, and the fabric of space itself is stretching. But Hubble had limitations. It primarily observed invisible and ultraviolet light. And here is the problem. The most distant, most ancient objects in the universe do not emit visible light. Or rather, they did, billions of years ago, but as the universe expanded, that light was stretched. The wavelengths got longer and longer as space itself expanded, shifting the light from visible wavelengths into the infrared. By the time the light from the very first galaxies reaches us, it has been stretched so far into the infrared that Hubble simply could not see it. It was invisible to Hubble, not because it was too faint, but because it was the wrong color. This is called cosmological redshift, and it is one of the most fundamental concepts in observational astronomy. Every photon of light traveling through the expanding universe gets its wavelength stretched by that expansion. The longer the light has been traveling, the more it has been stretched. Light from the very first galaxies, light that has been traveling for over 13 billion years, has been redshifted so dramatically that it now exists entirely in the infrared spectrum. To see the first stars, the first galaxies, the first light that ever illuminated the cosmos, you need a telescope that sees in infrared. You need a telescope with a much larger mirror to collect more of that incredibly faint, ancient light. And you need to put that telescope somewhere cold, somewhere dark, somewhere far from the thermal glow of the Earth. Because infrared light is essentially heat radiation, and any warmth near the telescope would drown out the signals from the distant universe. That is why scientists conceived of the James Webb Space Telescope. The idea was born in 1996. At that point, Hubble was already 6 years into its mission and was producing breathtaking results, but astronomers could see the limitations clearly. They knew there was a vast, unexplored era of cosmic history that lay just beyond Hubble's reach. They called it the Cosmic Dark Ages, the period between the release of the cosmic microwave background, which happened about 380,000 years after the Big Bang, and the formation of the first stars, which is thought to have occurred somewhere around 100 to 250 million years after the Big Bang. During that interval, the universe was filled with neutral hydrogen gas, and no stars had yet ignited. It was, quite literally, dark, no light sources existed anywhere. And then, slowly, the first stars began to form. The first nuclear furnaces ignited, and light returned to the cosmos for the first time since the Big Bang itself. This moment, this transition from darkness to light, is called the cosmic dawn. and seeing the cosmic dawn was the primary scientific motivation for building the James Webb Space Telescope. But building it was a nightmare. The original plan called for a launch around 2007, with a budget of about $1 billion. By the time the telescope was finally ready, the launch date had slipped to 2021, and the cost had ballooned to over $10 billion. Along the way, the project was nearly cancelled multiple times. Members of Congress questioned whether it was worth the expense. Engineers encountered problem after problem. The telescope's design was unlike anything ever attempted. Its primary mirror was 6.5 meters in diameter, nearly 3 times larger than Hubble's mirror, and it was made of 18 hexagonal segments coated in a thin layer of gold, because gold is an excellent reflector of infrared light. But a mirror that large could not fit inside any rocket fairing in its deployed configuration. So the engineers designed it to fold. The mirror would launch folded up and then unfurl in space, each segment locking into place with microscopic precision. And then there was the sunshield. To keep the telescope cold enough to detect faint infrared signals, it needed to be shielded from the heat of the sun, the earth and the moon. The solution was a sunshield the size of a tennis court, made of 5 layers of a material called kapton, each layer thinner than a human hair. This sunshield had to deploy flawlessly in the vacuum of space, stretching out from its folded configuration inside the rocket, without tearing, without tangling, without any single point of failure causing a catastrophe. And there were 344 of those single points of failure during the deployment sequence. 344 things that had to go exactly right, any one of which, if it failed, would have turned a $10 billion telescope into the most expensive piece of space debris in human history. The telescope was designed to orbit not the Earth, but a point in space called the second Lagrange point, or L2. This is a gravitational sweet spot about 1.5 million kilometers from Earth, on the side opposite the Sun. At L2, the telescope can keep its sunshield perpetually aimed at the Sun, while its mirror faces the cold darkness of deep space. But L2 is far away, far enough that if anything went wrong with the deployment, there would be no space shuttle mission to fix it, no astronaut crew sent to make repairs. With Hubble, when its mirror turned out to be slightly misshapen after launch, NASA sent astronauts to install corrective optics. With James Webb, there would be no second chances. Everything had to work the first time. On Christmas morning, December 25th, 2021, humanity held its collective breath. The James Webb Space Telescope launched aboard an Ariane 5 rocket from the Guiana Space Center in South America. The launch itself went perfectly. But the real terror was just beginning. Over the next 29 days, the telescope had to undergo its complete deployment sequence. Day by day, step by step, the sunshield unfolded, layer by layer, tensioned into position. The secondary mirror swung out on its boom. The primary mirror segments folded into their final configuration. Each step was monitored in real time by teams of engineers at the Space Telescope Science Institute in Baltimore and the Goddard Space Flight Center. And each step was accompanied by an almost unbearable level of anxiety. 29 days of heart attacks, as one NASA engineer later described it. And then, on January 24th, 2022, exactly 1 month after launch, James Webb fired its thrusters and slipped into its orbit around L2. Every deployment step had succeeded. Every mechanism had worked. 344 potential failure points, and not a single one had failed. The telescope was alive, it was functioning, and it was cooling down to its operating temperature of about -233 degrees Celsius, just 40 degrees above absolute zero. Over the following months, the mirror segments were painstakingly aligned. The instruments were calibrated. And then, on July 12, 2022, NASA released the first full-color images from the James Webb Space Telescope. The world saw them, and the world gasped. The first deep-field image, aimed at a galaxy cluster called SMACS 0723, showed thousands of galaxies stretching back to within about 1 billion years of the Big Bang. The detail was extraordinary. Galaxies that had appeared as smudges in Hubble's images were now resolved into clear spiral arms, bright cores, and delicate structures. And among them, behind them, magnified by the gravitational lensing of the foreground galaxy cluster, were some of the most distant galaxies ever observed. But the celebration did not last long. Because within weeks of those first images, as scientists began analysing the data in earnest, something strange emerged. Something deeply unsettling. The earliest galaxies that James Webb was observing were not what anyone had expected. They were too bright. They were too big. They were too structured. They were too massive, and they existed at a time in cosmic history when, according to every model, every simulation, every prediction of the standard model of cosmology, they simply should not have been there. The papers started flooding in. Teams at universities across the world, from the United States to Europe to Australia, independently analysing the James Webb data, all coming to the same disturbing conclusion. These galaxies were too much, too soon. And the phrase that began appearing in paper after paper, in press release after press release, was one that would come to define the James Webb era. Universe breakers. Now I need you to understand exactly why these galaxies were so shocking. And to do that, I need to explain what the standard model of cosmology actually predicts about how galaxies form. The standard model is called lambda CDM. Lambda refers to the cosmological constant, which is Einstein's term for dark energy, the force driving the accelerating expansion of the universe. CDM stands for cold dark matter, the invisible, undetectable substance that makes up about 27% of the total mass and energy of the cosmos. Together, lambda CDM is the framework that describes how the universe evolved from the Big Bang to the present day. It is the most successful cosmological model in history. It has correctly predicted the detailed structure of the cosmic microwave background, the distribution of galaxies on the largest scales, the abundance of light elements formed in the first few minutes after the Big Bang, and the accelerating expansion of the universe. For 3 decades, lambda CDM has passed test after test after test. It is the bedrock of modern cosmology. And lambda CDM makes very specific predictions about how galaxies form. According to the model, after the Big Bang, the universe was a nearly uniform soup of hot plasma. But it was not perfectly uniform. There were tiny fluctuations, microscopic differences in density from one region to another. Over hundreds of millions of years, gravity amplified these fluctuations. Regions that were slightly denser attracted more matter, growing denser still. Dark matter, which does not interact with light and therefore was not held back by radiation pressure, collapsed first, forming invisible halos. These dark matter halos then attracted ordinary matter, hydrogen and helium gas, which fell into the gravitational wells and began to cool and condense. Eventually, the densest pockets of gas collapsed to form the first stars. But this process was slow. Gas had to cool before it could collapse, and cooling takes time, especially for the primordial gas, which lacked heavy elements that can radiate heat efficiently. The first small proto-galaxies, according to the model, were tiny, maybe 1 million times less massive than the Milky Way. Over hundreds of millions of years, these proto-galaxies merged with each other, combining into larger and larger structures. This is called hierarchical assembly, and it is the cornerstone of galaxy formation theory. Small things merge to make bigger things, and bigger things merge to make even bigger things, like building a skyscraper one brick at a time. According to this model, truly massive galaxies, galaxies comparable in size and mass to our Milky Way, should not have appeared until the universe was at least 1 to 2 billion years old. There simply was not enough time before then for all the merging and growing and accumulating to produce something that large. And then James Webb looked into the early universe and found exactly that. Massive galaxies, right there, at a time when they had no business existing. Let me tell you about the most extreme example. It is called JADE's GS Z14-0. JADE stands for the J-West Advanced Deep Extragalactic Survey, one of the most ambitious observing programs ever conducted. GS refers to the Good South Field, a well-studied patch of sky, and Z14 refers to the galaxy's redshift, which is a measure of how much the light has been stretched by the expansion of the universe, and therefore a proxy for distance and age. A redshift of 14.32 means this galaxy's light has been travelling for so long that we are seeing it as it existed just 290 million years after the Big Bang. Let me say that again. 290 million years. The universe is currently about 13.8 billion years old. 290 million years is barely 2% of the universe's total age. If the entire history of the cosmos were compressed into a single year, this galaxy existed on January 3rd. And this galaxy, JADE's GS Z14-Nero, was not some dim, barely detectable smudge. It was bright. Surprisingly, shockingly bright. Its light was not coming from a single-point source like a quasar or an active black hole. It was extended, spread across a physical region, indicating that it was a real galaxy, with real stars producing real light. And the amount of light it was producing implied that it contained a substantial number of stars, far more than any model had predicted could exist at that early epoch. This galaxy is the most distant confirmed galaxy in the known universe. Its light has travelled 13.4 billion years to reach us. When that light was first emitted, the universe was a completely different place. It was smaller, denser, hotter, and filled with neutral hydrogen gas that had not yet been ionized by starlight. The cosmic dawn was just beginning. The first stars were only recently turning on, and yet somehow in this infant cosmos, a galaxy had already assembled itself to a degree that should not have been possible. But JADE's GS Z14-Nero was not alone. It was not a single oddity, a statistical fluke that could be explained away. Across multiple surveys, JADES, SEERS, the Cosmic Evolution Early Release Science Survey, Uncover, and others, James Webb kept finding them, galaxy after galaxy after galaxy at extreme redshifts, all of them brighter, more massive, and more structured than Lambda CDM predicted. The most famous case came from the SEERS survey, where a team led by researchers at several major universities identified 6 galaxies at redshifts between 7 and 9, corresponding to a time roughly 500 to 700 million years after the Big Bang. Each of these galaxies appeared to have stellar masses that were 10 to 100 times greater than what any model allowed. Some of them appeared to have stellar masses rivaling that of the present-day Milky Way. Rivaling. A galaxy that in the current universe has had 13.8 billion years to grow and accumulate stars was apparently matched in mass by galaxies that had only had a few 100 million years. It was as if you walked into a newborn nursery and found a fully grown adult sitting in one of the cribs. These 6 galaxies were dubbed the impossible galaxies. The media called them universe breakers, and the astrophysics community went into a state of controlled panic. Now I want to be careful here, because science is not about panic. Science is about evidence, analysis, and careful reasoning. And the first thing that scientists did, naturally, was to question the data. Were the redshifts correct? Were the mass estimates reliable? Could there be systematic errors in the analysis? The initial detections were based on photometric redshifts, which are estimates of distance based on the colours of a galaxy in multiple filters. Photometric redshifts are useful but imprecise. They can sometimes be wrong. A galaxy that appears to be at a very high redshift based on its colours might actually be a lower redshift galaxy with unusual dust properties, for example. So the first order of business was spectroscopic confirmation, which involves spreading a galaxy's light into a spectrum and identifying specific emission or absorption lines whose wavelengths can be precisely measured. Spectroscopic redshifts are far more accurate than photometric ones. And here is what happened. Some of the initial candidates turned out to be interlopers, Their redshifts were lower than initially estimated. They were not as distant, not as ancient, and not as problematic. This was expected. Whenever you cast a wide net, you catch some false positives. But many of the candidates were spectroscopically confirmed. Their redshifts were real, their distances were genuine. They really were sitting in the early universe, bright and massive and defiant. The mass estimates also came under scrutiny. When you estimate the mass of a distant galaxy, you are essentially measuring how much light it produces and then using models of stellar populations to infer how many stars must be present to produce that much light. But what if the light is not coming entirely from stars? What if some of it is coming from an actively feeding black hole at the galaxy's center, an active galactic nucleus or ANG, which can produce enormous amounts of radiation? If you mistake ANG light for starlight, you will overestimate the galaxy's stellar mass. This turned out to be part of the answer. Some of the impossible galaxies were not as massive as initially thought. Their light was being boosted by central black holes, making them appear more massive than they really were. This was a legitimate correction, and it reduced the severity of the crisis. But it did not eliminate it. Even after accounting for ANG contributions, many of the early galaxies remained more massive, more luminous, and more evolved than the models predicted. The discrepancy was reduced, but it did not go away. Stephen Finkelstein, an astronomer at the University of Texas at Austin, who has been at the forefront of this research, stated publicly that there is no crisis in terms of the standard model of cosmology. He argued that with updated stellar population models and better accounting for AGN activity, the impossible galaxies could be reconciled with lambda CDM. But not everyone in the field agrees. Many researchers believe that while the most extreme claims have been walked back, the overall population of early galaxies observed by James Webb still represents a significant tension with the standard model. The early universe was more active, more productive, and more efficient at forming stars and building galaxies than lambda CDM naturally predicts. And then, in January of 2026, came a discovery that made the problem even more vivid and immediate. A team of astronomers at Texas A&M University, led by Dr. Wada Hu and Dr. Casey Papovich, published a paper in the journal Nature Astronomy announcing the discovery of something extraordinary. Using James Webb data from the JADE survey, they had identified a system of at least 5 galaxies, all in the process of merging together at a redshift of 6.71. This corresponds to a time about 800 million years after the Big Bang. They called it Joubelest's Quintet. Now, galaxy mergers are not unusual in the present-day universe. Our own Milky Way is currently engaged in a slow-motion collision with the Andromeda Galaxy, and the two will fully merge in about 4.5 billion years. But a 5-way merger involving multiple galaxies at that early epoch? That was not supposed to happen. At 800 million years after the Big Bang, the standard models predict that galaxies should still be relatively small and isolated. The universe was still young, structures were still forming. Complex multi-galaxy merger events were thought to become common only after about 1 billion years or more. Yet here was an entire system of 5 galaxies, crammed into an unusually compact region of space, all interacting, all merging, all going through a violent gravitational dance that was reshaping their environments. But the merging itself was not even the most shocking part. What stunned the researchers was what they found around the galaxies. There was a halo of glowing gas, extending far beyond the boundaries of the individual galaxies, emitting light from ionized oxygen and hydrogen. This gas was enriched. It contained heavy elements that can only be produced inside stars through nuclear fusion. Oxygen in particular is not something you find floating around in the primordial universe. It has to be made. Stars have to form, live out their lives, and then explode or shed their outer layers, releasing these heavy elements into the surrounding space. And for those elements to exist outside the galaxies, they had to be ejected, either by powerful stellar winds, supernova explosions, or, as the Texas A&M team concluded, by the gravitational interactions of the merger itself. The implications were staggering. This meant that not only were galaxies forming faster than expected, not only were they engaging in complex multi-body mergers earlier than expected, but stars within those galaxies had already gone through their entire life cycles, producing heavy elements and distributing them into the intergalactic medium. The chemical enrichment of the universe was well underway at a time when models said it should have barely begun. The system's star formation rate was measured at approximately 250 solar masses per year. To put that in perspective, our Milky Way forms new stars at a rate of about 1 to 2 solar masses per year. Driscoll's quintet was producing stars more than 100 times faster than our galaxy does today, and it was doing this 800 million years after the Big Bang. Dr. Popovich was remarkably candid in his assessment. He said, and I quote, "By showing that a complex merger-driven system exists so early, it tells us our theories of how galaxies assemble and how quickly they do so need to be updated to match reality." Need to be updated to match reality. That is a diplomatically worded way of saying our models got it wrong. And there is a downstream implication that makes this even more significant. James Webb has identified a growing number of massive galaxies at slightly later times, around 2 to 3 billion years after the Big Bang, that appear to be largely inactive. They are massive, but they are not forming new stars. They are red and dead, as astronomers say. How did these galaxies get so massive if they had already stopped making stars so early? One possible answer is that systems like Driscoll's quintet merged rapidly, consumed their gas reserves in a frenzy of star formation, and then ran out of fuel. They burned too bright, too fast, and went dark. If this interpretation is correct, then the entire timeline of galaxy evolution needs to be compressed and accelerated, with major events happening much earlier than any current model predicts. So galaxies formed too fast. Stars formed too fast. Heavy elements appeared too fast. The structure of the early universe was far more complex, far more evolved, and far more active than anyone had predicted. But that was just the beginning. Because James Webb also found something inside these early galaxies that made the crisis even worse. Lurking at the centers of some of these impossibly early galaxies were monsters. Supermassive black holes with masses of millions, even tens of millions of solar masses. And they were actively feeding, consuming matter at ferocious rates, growing at speeds that our physics simply cannot account for. To understand why this is so alarming, let me first give you a foundation on what black holes are and how they are supposed to grow. A black hole is a region of space where gravity is so intense that nothing, not even light, can escape once it crosses a boundary called the event horizon. At the center of the black hole, all of the mass is compressed into an infinitely dense point called a singularity, at least according to general relativity. We suspect that the singularity is actually described by some yet unknown theory of quantum gravity, but that is a discussion for another day. Black holes come in different sizes. Stellar mass black holes are the remnants of massive stars that have exhausted their nuclear fuel and collapsed. These typically have masses between about 5 and 50 times the mass of our Sun. Then, at the other end of the spectrum, there are supermassive black holes, which have masses ranging from millions to billions of solar masses. These supermassive black holes sit at the centers of virtually every large galaxy in the universe, including our own Milky Way, which hosts a supermassive black hole called Sagittarius A star, with a mass of about 4 million solar masses. The mystery of supermassive black holes is not whether they exist. We know they do. We have imaged the shadows of 2 of them directly using the Event Horizon Telescope. The mystery is how they got so big. Because going from a stellar mass black hole of, say, 20 solar masses to a supermassive black hole of 100 million solar masses requires an enormous amount of growth. And that growth is not unlimited. There is a physical limit to how fast a black hole can eat. This limit is called the Eddington limit. Here is how it works. As matter falls toward a black hole, it forms an accretion disk, a swirling disk of superhot gas and dust spiraling inward. As this material spirals closer to the event horizon, it gets compressed and heated to extreme temperatures, emitting enormous amounts of radiation, X-rays, ultraviolet light, and other energetic photons. This radiation creates an outward pressure that pushes against the infalling material. The Eddington limit is the point at which the outward radiation pressure exactly balances the inward pull of gravity. If the black hole tries to eat faster than the Eddington rate, the radiation pressure blows the incoming material away, effectively cutting off the food supply. This means there is a maximum speed at which a black hole can grow through normal accretion. And when you do the math, starting from a stellar mass seed black hole and growing at the Eddington rate continuously, which is itself an optimistic assumption, because black holes do not always have access to food and do not always eat at maximum capacity. It takes about 800 million years to reach supermassive status. 800 million years of non-stop, maximum efficiency eating. And here is where James Webb dropped the bombshell. JWST found confirmed actively growing supermassive black holes in galaxies that existed just 570 million years after the Big Bang. 570 million years, that is 230 million years less than the absolute theoretical minimum required for a stellar mass seed to grow to supermassive size by normal accretion. It is like finding a 1,000-year-old tree in a forest that was planted 5 years ago. But it gets worse. These black holes were not just present, they were enormous relative to their host galaxies. In the local universe, there is a well-established scaling relationship between the mass of a supermassive black hole and the mass of its host galaxy's central bulge. The black hole is typically about 0.1% of the galaxy's total stellar mass, but the early universe black holes found by James Webb were 10 to 100 times more massive than this scaling relation would predict. They were disproportionately huge, dominating their small, young host galaxies in a way that does not match any observation in the nearby universe. Dr. George Reiki, a Regents Professor of Astronomy at the University of Arizona and one of the leading figures in JWST science, put it bluntly. He said, "GWST has shown that our ideas about how supermassive black holes formed were pretty much completely wrong. Pretty much completely wrong." Coming from one of the most respected astronomers in the world, those are extraordinary words. So how do you explain black holes that are too massive too early? You need a new mechanism for creating them, and the leading candidate is called direct collapse. The standard story of black hole formation goes like this. A massive star lives out its life, exhausts its nuclear fuel, and its core collapses to form a stellar mass black hole. This seed then grows over time by accreting matter. But what if some black holes did not start as stars at all? What if, in certain rare conditions in the early universe, massive clouds of primordial gas, instead of fragmenting into stars, collapsed directly into black holes? If a gas cloud is massive enough and can avoid fragmenting, which requires it to remain warm and not cool too efficiently, it could collapse into a single object with a mass of 10,000 to 100,000 solar masses. No star phase, no supernova, just a direct gravitational collapse from gas cloud to black hole in one step. Direct collapse black holes were once considered a theoretical curiosity, an exotic possibility that most astrophysicists thought was unlikely to occur in practice. The conditions required seemed too specific. You needed a massive gas cloud with almost no heavy elements to prevent efficient cooling, and you needed a nearby source of ultraviolet radiation to keep the gas warm and suppress fragmentation. Finding all of these conditions simultaneously in the early universe seemed implausible. But James Webb's observations have changed the calculus. The data now suggests that the early universe was teeming with supermassive black holes that could not have formed through normal stellar collapse and accretion. The direct collapse scenario, once exotic, now appears almost necessary. It may be the only way to explain what we see. And in December of 2025, a discovery made this even more dramatic. JWST revealed what researchers called a cosmic shapeshifter in the early universe, an object that challenges prevailing theories about how supermassive black holes and galaxies grew together. Before JWS, the dominant paradigm was co-evolution, the idea that black holes and their host galaxies grow in lockstep, feeding on the same gas supply and regulating each other's growth through feedback mechanisms. The cosmic shapeshifter suggested that this tidy picture was wrong. The black hole and its host galaxy were wildly mismatched, with the black hole far too massive for the galaxy it inhabited, suggesting that the black hole may have formed first and the galaxy assembled around it later. Think about what that means. For decades we assumed that galaxies formed first and then developed black holes at their centers, like a city growing and eventually building a central government building. But GWS data suggests the opposite may be true. The black holes came first and the galaxies formed around them, like a government building being erected and a city spontaneously appearing around it. This flips our entire understanding of cosmic structure formation on its head. The early universe, as James Webb is revealing it, was a far more violent, more extreme, and more mysterious place than any model had predicted. Massive galaxies that should not exist. Supermassive black holes that should not exist. And now we come to the most bizarre discovery of all. The objects that defied classification for years, the objects so strange that scientists could not even agree on what category of celestial object they belonged to. The little red dots. This is where the story takes its most unexpected turn. And to understand it, we need to go back to the very earliest surveys conducted by James Webb. Starting in 2022, as James Webb's first deep survey data began flowing in, astronomers noticed something peculiar. Scattered across the images of the early universe, mixed in among the galaxies and stars and foreground objects, were tiny, compact, extremely red objects. They were small, they were bright, and they were everywhere. Hundreds of them appeared in survey after survey, Sears, Jades, Uncover, and others. They were far more numerous than anyone had predicted any particular class of object should be at those early epochs, and they were puzzling because they did not neatly fit into any existing category. Scientists began calling them little red dots, a charmingly informal name for objects that would cause years of headaches and debate in the astronomical community. Let me explain why they were so confusing. The redness of an astronomical object can mean several things. It can indicate a population of old, cool stars, the kind you find in elliptical galaxies that stopped forming new stars long ago. It can indicate heavy dust obscuration, where dust between us and the object absorbs bluer light and lets redder light pass through. Or it can indicate extreme redshift, where the light has been shifted so far into the red that the object appears red simply because of the expansion of the universe. For the little red dots, the redness seemed to suggest massive stellar populations. If you interpreted the light as coming from stars, you needed a lot of stars. Very old stars, packed into a very small volume. This implied that each little red dot was a massive, compact galaxy. Possibly an ancient galaxy that had already formed all of its stars and was now sitting there quietly. But this interpretation created an immediate paradox. The little red dots appeared at about 600 million years after the Big Bang. There simply had not been enough time to form that many stars, let alone for those stars to age and redden. The little red dots seemed to demand even more impossibly massive galaxies than the universe breakers, and packed into even smaller volumes. It was as if the universe was playing a trick. Every time scientists thought they understood the impossible galaxies problem, a new class of objects appeared that made it even worse. And so, the debate began. For 3 years, from 2022 to 2025, the astrophysics community argued vigorously about what the little red dots were. Multiple hypotheses were proposed, tested, and debated. The first hypothesis was the simplest. These were genuinely ancient, massive galaxies. Compact red ellipticals that had formed incredibly early and had already shut down their star formation. But this hypothesis had a serious problem. If these were real massive galaxies, there should be descendants of them in the more recent universe. As the universe evolved, these galaxies should have grown, merged with others, and become the giant elliptical galaxies we see today. But when astronomers looked at the numbers, there were too many little red dots. Far more than could be accounted for by the number of giant ellipticals in the present-day universe. Where did they all go? The numbers did not add up. The second hypothesis was that these were active galactic nuclei, quasars or quasi-stellar objects powered by supermassive black holes actively consuming matter. The accretion disks around these black holes can produce enormous amounts of light, and if the systems were heavily obscured by dust, they might appear red. This hypothesis was promising because it could explain the compactness and the extreme luminosity. A single accreting black hole can outshine an entire galaxy, and if it is dust obscured, it would appear red. But there was a problem with this hypothesis too. Typical AN and quasars are strong X-ray emitters because the hot gas in the accretion disk produces copious X-ray radiation. But when astronomers checked, the little red dots were faint in X-rays, barely detectable or not detectable at all. Where were the X-rays? A third hypothesis proposed that the little red dots were not galaxies at all, but rather baby galaxies under construction. Specifically, they might be globular clusters in the process of forming dense knots of stars condensing out of gas in the early universe. This was a creative idea, but it struggled to explain the extreme redness and the luminosities observed. And then a fourth hypothesis emerged, one that would eventually prove to be the most compelling. What if the little red dots were a type of object that had never been observed before? What if they were not galaxies in the traditional sense, and not classical quasars either, but something in between? What if they were supermassive black holes, rapidly accreting matter, but surrounded by a thick, dense cocoon of hot, partially ionized gas that absorbed and reprocessed the radiation from the accretion disk? This model came to be known as the black hole star model, abbreviated as BHH star. The idea is elegant, and it addresses the key puzzles. A rapidly accreting supermassive black hole at the center produces enormous amounts of high-energy radiation, X-rays and ultraviolet light. But instead of escaping into space as it would in a normal quasar, this radiation runs into a dense, layered gas cocoon surrounding the black hole. The gas cocoon absorbs the X-rays and ultraviolet light and reprocesses it, re-emitting it at longer wavelengths in the infrared. This explains why the little red dots appear red. The light has been shifted to longer wavelengths by the gas cocoon. This explains why they are compact. The emission comes from a single central engine, not from a spread-out galaxy. This explains why they are X-ray faint. The gas cocoon absorbs the X-rays before they can escape. And this explains why they appear to have enormous stellar masses if you naively interpret the light as coming from stars, because the reprocessed light mimics the spectral signature of old stellar populations. This hypothesis was compelling from the moment it was proposed, but it needed proof. It needed a smoking gun, a single little red dot observed in such extraordinary detail that every prediction of the BH star model could be tested against the data. And in June of 2026, that smoking gun was found. A team of astronomers led by Vasily Kokorev at the University of Texas at Austin published a groundbreaking paper in the Astrophysical Journal. They had obtained the deepest spectrum ever taken of a little red dot, an object designated Glimpse 17775, and the results were stunning. Let me tell you the story of how this observation came about, because it involves a beautiful piece of cosmic luck. The primary goal of the James Webb observation program was not to study little red dots at all. The program, called Glimpse, was designed to search for population 3 stars, the very first generation of stars that formed in the universe, made of pure hydrogen and helium with no heavier elements. Population 3 stars are the holy grail of stellar astrophysics, and no one has ever confirmed a direct observation of one. The Glimpse program targeted the galaxy cluster Abell SO63, a massive cluster of galaxies whose immense gravitational field bends and magnifies the light from objects behind it, a phenomenon called gravitational lensing. And it was behind Abell SO63 magnified by its gravitational lens, that Glimpse 1sin775 happened to sit. It was a little red dot at a cosmological redshift of 3.5, meaning it existed about 1.8 billion years after the Big Bang. It was not the most distant little red dot ever found, but it had something far more valuable than extreme distance. It was magnified. The gravitational lensing of Abell S163 amplified the light from Glimpse 1sin775, acting like nature's own magnifying glass. This meant that the 30 hours of spectrum that James Webb collected was effectively equivalent to 80 hours of telescope time. The level of detail was unprecedented. When Kokarev and his team analyzed the spectrum, they found more than 40 distinct spectral lines. 40 lines. From a single little red dot. No other little red dot had ever yielded anything close to this level of spectral detail. It was like having a blurry photograph suddenly come into perfect focus, and every single one of those 40-plus lines was consistent with the black hole star model. Let me walk you through the key evidence, because this is where the science gets truly beautiful. First, the hydrogen, oxygen, and helium emission lines. In a simple model where you have a rotating cloud of gas, perhaps a galaxy or a normal accretion disk, these lines would have a characteristic shape, broadened by the rotation of the gas, what astronomers call Doppler broadening. But the lines in Glimpse 1sin775 did not fit this simple model. Instead, the best fit required an additional broadening mechanism called electron scattering. Electron scattering occurs when photons of light bounce off free electrons in a dense gas. The photons get randomly redirected, which broadens the spectral lines in a distinctive way. This is a telltale signature that the light is passing through a dense, layered gas cocoon before reaching us. Exactly what the BH star model predicts. Second, the ion lines. The team detected 16 distinct ion emission lines in the spectrum, a feature so striking that they dubbed it an ion forest. Iron is an element that requires extreme conditions to produce and excite. The strength and ratios of these ion lines, relative to each other and to other elements in the spectrum, demanded a powerful, high-energy source. A rapidly accreting supermassive black hole fits the bill perfectly. A population of stars, even hot stars, would not produce the energy needed to create this ion forest. Third, the helium lines showed something remarkable. The spectrum contained evidence of both helium fluorescence and helium absorption. Fluorescence occurs when atoms absorb high-energy radiation and re-emit it at specific wavelengths. Absorption occurs when atoms intercept light and remove specific wavelengths from the spectrum. Both of these processes, occurring simultaneously, independently confirm that there is a dense medium surrounding a powerful energy source. The helium atoms are both absorbing radiation from the central engine and being excited to fluoresce by it. This is precisely the behavior you would expect from a gas cocoon enveloping a rapidly feeding black hole. Fourth, the oxygen lines. Certain ratios of oxygen emission lines are diagnostic of the physical conditions in the emitting gas, its temperature, density, and the energy of the radiation field illuminating it. The oxygen line ratios in Glimpse 1sin775 were consistent with a high-energy, high-density environment, not with a typical galaxy or stellar population. Every piece of evidence pointed in the same direction. Every spectral line, every line ratio, every broadening mechanism, it all fit. Glimpse 1sin775 was a supermassive black hole, actively devouring matter at a prodigious rate, wrapped in a thick cocoon of hot, dense, partially ionized gas. This gas cocoon was absorbing the X-rays and ultraviolet light from the accretion process and re-emitting it in the infrared, producing the distinctive red color and the spectral signatures observed. But there was one more piece of the puzzle. The team combined the James Webb data with archival observations from the Hubble Space Telescope, from the Frontier Fields and Buffalo programs that had previously observed the Abell 1063 cluster. And when they did, they discovered that Glimpse 1sin775 was not sitting alone. It was surrounded by a giant host galaxy. This host galaxy was producing blue light from young stars, which, when added to the red light from the black hole star itself, explained why the Balmer break, a characteristic dip in the spectrum that is a hallmark of little red dots, was weaker in glimpse 1C775 than in other little red dots. The host galaxy's blue starlight was partially filling in the dip. Kokorev's reaction to these results was notable for its quiet confidence. He said, "Everything fits. Nothing is broken. And I think that makes the puzzle that is our universe even better. Everything fits. Nothing is broken." These words carry enormous weight. For years, the little red dots had been held up as potential evidence that cosmology was in crisis, that something fundamental was wrong with our understanding of the universe. If these objects were really impossibly massive galaxies that had formed too early, then Lambda CDM had a serious problem. But the BH star interpretation removes that particular crisis. The little red dots are not impossibly massive galaxies. They are rapidly feeding supermassive black holes wrapped in gas cocoons. Their apparent stellar masses were a misinterpretation. The light was not coming from stars. It was coming from reprocessed radiation from a central black hole engine. So this is good news, right? Crisis averted? Not exactly, because while the BH star model solves one problem, it creates another. If the early universe was teeming with little red dots, and if little red dots are rapidly accreting supermassive black holes, then the early universe was teeming with supermassive black holes. And that brings us right back to the question we confronted earlier. How did all of those supermassive black holes form so quickly? The BH star model does not require the black holes to be as massive as if you interpreted the little red dots as stellar populations, but it still requires them to be supermassive, and it requires them to exist in abundance at very early times. Moreover, the sheer number of little red dots suggests that this was not a rare phenomenon. This was not a handful of unusual objects. There were hundreds of them in the survey data, and extrapolating to the full sky implies that there were enormous numbers of rapidly feeding supermassive black holes in the early universe. The cosmic dawn was not the gentle, gradual process that textbooks described. It was a violent, chaotic era dominated by black hole activity on a scale that no one had imagined. In August of 2025, a major study using James Webb data identified approximately 300 little red dots in a single survey, and the researchers noted that these objects may not be galaxies at all, anticipating the BH star interpretation that would be confirmed months later with Glimpse Sun 775. And in February of 2026, another team published results connecting the little red dots specifically to direct collapse black holes, the very formation mechanism we discussed earlier. According to their analysis, the properties of the little red dots, their luminosities, their spectral characteristics, their abundance, are all consistent with a population of direct collapse black holes that formed in the first few 100 million years after the Big Bang and were observed in their active feeding phase. So the picture that is emerging is this: the early universe, far from being a quiet, dark place where structures slowly assembled over billions of years, was a cosmic battlefield. Massive gas clouds were collapsing directly into supermassive black holes. Those black holes were voraciously consuming matter, surrounded by dense gas cocoons that made them appear as mysterious little red dots. Some of these systems were already embedded in host galaxies. Others may have been the seeds around which galaxies would later form. And the entire process was happening far earlier and far more vigorously than any model had predicted. This is fundamentally different from the picture of the cosmic dawn that existed before James Webb. It is a picture that is simultaneously more exciting and more troubling. More exciting because it reveals a universe that was dynamic and complex from its earliest moments. More troubling because it means our models of early cosmic evolution were significantly wrong. If you have made it this far, then I know you are the kind of person who craves deep understanding, and I respect that enormously. If you are learning something new, take a second and hit that like button. It is such a simple action, but it makes a massive difference. It helps this video reach more curious minds who are hungry for this kind of content, and I would love to hear from you in the comments. Tell me, did you know about little red dots before this video? Did you know that the objects astronomers thought were impossible galaxies might actually be black holes wrapped in gas? Let me know, because now we're about to enter what I consider the most unsettling territory of all. We are going to leave the early universe behind and confront a crisis that affects the entire cosmos, past, present, and future. We are going to talk about the Hubble tension. If I told you that the universe is expanding, you would probably nod. This has been common knowledge since the late 1920s. But if I told you that the universe is expanding at two different speeds at the same time, depending on how you measure it, you would probably think I was joking. I am not. This is one of the most profound crises in the history of physics, and it has a name. It is called the Hubble tension, and James Webb was supposed to resolve it. Instead, JWST made it worse. Let me start from the beginning. In 1929, an astronomer named Edwin Hubble made one of the most important observations in the history of science. By studying the light from distant galaxies, he discovered that nearly all galaxies are moving away from us, and that the more distant a galaxy is, the faster it is receding. This relationship, velocity equals a constant times distance, is called Hubble's law, and the constant in that equation is called the Hubble constant, denoted h0. The Hubble constant is not just a number, it is arguably the single most important parameter in all of cosmology. If you know h0, you can calculate the age of the universe, you can calculate its size, you can determine its geometry, its density, and its ultimate fate. Everything in cosmology is tied to this one number. Getting it right is not optional, it is essential. For decades, measuring the Hubble constant was one of the primary goals of observational cosmology. And there are fundamentally two different ways to measure it. The first method is called the cosmic distance ladder. It is a local measurement based on observing objects in the relatively nearby universe. The distance ladder works like this. You start by measuring the distances to objects that are close enough for direct measurement using techniques like parallax, where you measure the apparent shift in a star's position as the Earth orbits the Sun. Then, you use those nearby objects to calibrate the brightness of a class of standard candles, objects whose intrinsic luminosity is known. The most important standard candles for the first rungs of the ladder are Cepheid variable stars. Cepheids are pulsating stars whose period of pulsation is directly related to their intrinsic brightness. By measuring a Cepheid's period, you can determine its true brightness, and by comparing that to how bright it appears, you can calculate its distance. Cepheids can be observed out to tens of millions of light years, but to measure h0, you need distances far beyond what Cepheids can reach. So you use Cepheids to calibrate the next rung of the ladder, Type 1a supernovae. A Type 1a supernova occurs when a white dwarf star, the dense remnant of a dead star, accretes matter from a companion star until it reaches a critical mass and detonates in a thermonuclear explosion. These explosions have a remarkable property: their peak brightness is standardizable. By observing the shape of their light curve, how the brightness rises and falls over time, you can determine their intrinsic luminosity. This makes them excellent standard candles that can be seen at distances of billions of light years. By combining Cepheid distances with Type 1a supernova distances, you can measure the expansion rate of the universe directly. This is what the SHO 0 ES team, Napa no Hatenova H-Nero for the equation of state, led by Nobel laureate Adam Riess, has been doing for years. Their result, refined over multiple iterations, is that H0 equals approximately 73 kilometers per second per megaparsec. This means that for every megaparsec of distance, which is about 3.26 million light years, a galaxy is moving away from us at an additional 73 kilometers per second. But there is another, completely independent way to measure H0, and this is where the trouble starts. The second method uses the cosmic microwave background, the CMB, The CMB is the oldest light in the universe, released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely for the first time. The CMB carries an extraordinary amount of information about the early universe, including its density, composition, and geometry. Encoded in tiny temperature fluctuations across the sky, the European Space Agency's Planck satellite made the most precise measurements of these fluctuations ever achieved. Now here is the key. The CMB does not directly tell you the current expansion rate. What it does is give you a snapshot of the universe at 380,000 years of age, along with enough information to predict how the universe should have evolved from that point to the present day, assuming the lambda CDM model is correct. When you take the Planck CMB data and run it through the lambda CDM model, it predicts that the Hubble constant today should be approximately 67.4 kilometers per second per megaparsec, 67.4 versus 73. That is a difference of about 9%. And in precision cosmology, 9% is not a small discrepancy. It is enormous. Think about it this way. You have two extremely precise methods for measuring the same quantity. Both methods have been refined over decades by the best scientists in the world using the best instruments available, and they give two different answers, not because one is measured poorly, because both are measured with incredible precision. The error bars on both measurements have been shrunk to the point where they do not overlap. There is no measurement uncertainty large enough to explain the discrepancy. This means one of three things. Either one or both measurements have a systematic error that nobody has been able to identify despite years of searching, or the lambda CDM model, which is used to predict H0 from the CMB, has a flaw. Or there is new physics, some undiscovered component of the universe that affects the expansion rate in a way that is not captured by the current model. For years, many cosmologists hoped it was the first option, a systematic error. Maybe the Cepheid measurements were slightly off. Maybe there was some unrecognized source of uncertainty in the supernova data. Maybe the Planck data had a subtle bias. But as more and more independent measurements were made, using different techniques, different calibrators, different telescopes, the tension stubbornly refused to go away. It kept growing. And then James Webb entered the picture. One of the major anticipated contributions of JEST to cosmology was its ability to sharpen the cosmic distance ladder. Hubble Space Telescope had been used for decades to observe Cepheid variable stars in galaxies that also hosted Type Ia supernovae, but at great distances, Hubble's resolution was insufficient to cleanly separate individual Cepheid stars from the crowded backgrounds of their host galaxies. This blending, where the light of a Cepheid is contaminated by the light of nearby stars, could introduce systematic errors in the distance measurements. James Webb, with its sharper infrared vision and larger mirror, could resolve individual stars far more cleanly, potentially eliminating this source of uncertainty. The expectation was that James Webb would either confirm the Ashneries value of 73, validating the tension and forcing a rethinking of the standard model, or it would revise the Cepheid distances downward, bringing the local measurement closer to 67.4 and resolving the tension. Either way, JEPST was supposed to settle the debate. It did not settle anything. What happened instead was that different teams using James Webb data reached different conclusions, and the debate became even more intense. Wendy Friedman, a distinguished astronomer at the University of Chicago and the leader of the Chicago Carnegie Hubble Program, or CCP, used JEST data to measure distances using the tip of the red giant branch, or TrgB method. TrgB is an alternative to Cepheids as a distance indicator. Red giant stars in a galaxy reach a maximum luminosity before they undergo a helium flash and transition to a different evolutionary stage. This maximum luminosity, the tip of the red giant branch, is remarkably consistent across different galaxies, making it a good standard candle. Friedman's team used JWST observations of TrgB stars in multiple galaxies to calibrate the distance ladder and arrived at a value of approximately 70.4 kilometers per second per megaparsec. 70.4, right in between the two competing values. Friedman's team argued that this result was consistent with the CMB prediction of 67.4, once uncertainties were accounted for, and that the Hubble tension was therefore resolved, or at least significantly reduced. But this claim was immediately challenged. Dan Skolnick, an astrophysicist at Duke University and one of the leading experts on the Hubble tension, pointed out that Friedman's team had excluded several supernovae from their sample that they could have included. Xiang Li of Johns Hopkins University, working with Skolnick, published a paper showing that if you used Friedman's own ChirGB measurements but included the complete sample of supernovae, the value of H0 went back up to the higher range, around 73. The resolution claimed by Friedman's team, Skolnick argued, was an artifact of an incomplete analysis. And then another team, led by Joe Jensen at Utah Valley University, used a completely different method with JWS data. Jensen's team measured something called surface brightness fluctuations, or SBF. This is a statistical technique that exploits the graininess of a galaxy's light. When you observe a galaxy, its surface brightness is the sum of light from all the stars in each pixel of the image. In nearby galaxies, the light is grainier because individual stars contribute noticeably to each pixel. In more distant galaxies, the light is smoother because each pixel contains the blended light of many more stars. By quantifying this graininess, you can estimate the distance to the galaxy. Jensen's team used JWEST images to measure the SBF of 14 elliptical galaxies, then used those to calibrate distances to 60 more distant ellipticals, and from that derived a value of H0 of 73.8 kilometers per second per megaparsec. 73.8. Right in line with the Shek0 value, and Jensen's team used neither Cepheids nor Type 1a supernovae, eliminating both of the calibrators that Friedman's team had suggested might be sources of systematic error, yet the tension remained. And then there is TDCosmo, a consortium that uses an entirely independent method based on gravitational lensing of quasars. When light from a distant quasar passes near a massive foreground galaxy, the gravitational field of the galaxy bends the light, creating multiple images of the quasar. These images arrive at slightly different times because the light paths have different lengths. By measuring these time delays and modelling the mass distribution of the lensing galaxy, you can determine the expansion rate of the universe. This method uses no Cepheids, no supernovae, no TrGB stars. It is completely independent of the cosmic distance ladder. The TDCosmo consortium spent 6 years rigorously reanalyzing their data, testing for systematic errors, and subjecting their methodology to every possible scrutiny. Their final result, published in 2025, was 72.1 kilometers per second per megaparsec. Again, strongly supporting the higher value. Again, confirming the tension. At the meeting of the American Astronomical Society in January 2025, Dan Skolnick took the stage and made a declaration that sent shockwaves through the community. The Hubble tension, he said, is now a crisis, and by early 2026, the evidence had only strengthened. A massive consortium of over 500 researchers called Cosmoverse published a comprehensive white paper analysing all available measurements of H0. The paper's conclusion was stark. The vast majority of local measurements cluster around 73 kilometers per second per megaparsec, with varying uncertainties. The gap between the local value and the CMB prediction is real, robust, and persistent. Multiple independent methods, multiple independent teams, multiple independent telescopes, all telling the same story. The universe is expanding faster than the standard model says it should be. The statistical significance of this discrepancy has reached and exceeded 5 sigma, which is the threshold that physicists use to declare a genuine discovery. A 5 sigma result means there is less than a 1 in 3.5 million chance that the discrepancy is a statistical fluke. In particle physics, 5 sigma is what was required to confirm the discovery of the Higgs boson. In cosmology, 5 sigma is what is now being attached to the Hubble tension. But what does it mean? If the tension is real, if it is not due to some subtle measurement error, then there is something fundamentally wrong with our understanding of the universe. The lambda CDM model, which has been the gold standard of cosmology for 3 decades, makes a prediction about the expansion rate that does not match reality. Something is missing from the model. Some ingredient, some physical process, some component of the universe that we have not yet identified is affecting the expansion rate in a way that our current framework does not account for. Multiple ideas have been proposed. One of the most prominent is early dark energy, the idea that there was a brief burst of additional dark energy in the first few 100,000 years after the Big Bang, which sped up the expansion slightly during that early epoch before fading away. This extra kick would change the prediction derived from the CMB, potentially bringing it into agreement with the local measurements. Another idea involves new particles, perhaps a new type of neutrino or some form of dark radiation, particles that interact only through gravity and that contribute to the energy density of the early universe without being directly detectable. Yet another idea involves modifications to Einstein's general relativity, the possibility that gravity works slightly differently on cosmological scales than Einstein's equations predict. Each of these ideas is radical. Each would require a fundamental revision of our understanding of physics. And none of them has been confirmed or ruled out. The Hubble tension remains an open wound in cosmology, a clear signal that something is wrong or missing, but without a clear solution. Jensen, despite being in the thick of the debate, maintained a measured perspective. He said, "It is important to remember that the uncertainties put us in only mild disagreement. I expect that we will soon know if the disagreement can be explained by the mundane choices of calibration galaxies and processing techniques. But if it cannot, then the inescapable conclusion is that there is something wrong with our understanding of the universe. And figuring that out could be the next great quest in cosmology." The Hubble tension is one crack in the foundation of lambda CDM, but it is not the only one. Because while astronomers have been arguing about how fast the universe is expanding, an entirely different group of scientists has been quietly accumulating evidence for something even more unsettling, something that strikes at the very heart of what drives the expansion in the first place. The dark energy that makes up 68% of the total energy of the universe, the mysterious force that is pushing space apart at an accelerating rate, may be dying. To understand how terrifying this is, let me take you back to 1998. In that year, 2 independent teams of astronomers, led by Saul Perlmutter and by Brian Schmidt and Adam Ries, made one of the most shocking discoveries in the history of science. They were measuring the distances to distant Type 1a supernovae, expecting to find that the expansion of the universe was slowing down. After all, gravity is attractive. Every galaxy in the universe pulls on every other galaxy. This gravitational attraction should be decelerating the expansion, like a ball thrown upward, gradually slowing down before it falls back. But that is not what they found. The distant supernovae were dimmer than expected, meaning they were farther away than the models predicted. The expansion of the universe was not slowing down. It was speeding up. Something was pushing the universe apart, overcoming the attractive pull of gravity and driving the expansion to accelerate. This discovery earned Perlmutter, Schmidt, and Ries the Nobel Prize in Physics in 2011, and the mysterious something driving the acceleration was given a name: dark energy. Dark energy is, by most measures, the most important and least understood component of the universe. It makes up about 68% of the total energy content of everything that exists. Ordinary matter, the stuff that makes up stars, planets, people, everything you can see and touch, makes up only about 5%. Dark matter, the invisible gravitational scaffolding that holds galaxies together, makes up about 27%. And dark energy, the force driving the accelerating expansion, makes up the rest. But what is dark energy? The simplest and most elegant answer comes from Einstein himself. In his equations of general relativity, there is a mathematical term called the cosmological constant, represented by the Greek letter lambda. Einstein originally introduced this constant to prevent his equations from predicting a dynamic universe, because at the time, in the early 20th century, most scientists believed the universe was static. When Hubble discovered the expansion of the universe, Einstein removed the cosmological constant, calling it his greatest blunder. But decades later, the discovery of the accelerating expansion brought it back. The cosmological constant can be interpreted as the energy of empty space, or vacuum energy. According to quantum physics, even the most perfect vacuum is not truly empty. It seethes with virtual particles popping in and out of existence, a quantum froth of creation and annihilation that gives space itself a baseline energy. On small scales, this energy is negligible, but on cosmic scales where there is an enormous amount of space, this vacuum energy adds up and produces a repulsive gravitational effect, pushing space apart. If dark energy is the cosmological constant, then it has a very specific property: it is constant. It does not change over time. It does not weaken or strengthen. Every cubic meter of space has the same dark energy density today as it did 1 billion years ago and will 1 billion years from now. And as the universe expands and more space is created, the total amount of dark energy increases proportionally. This means the expansion not only continues but accelerates, because there is more and more dark energy driving it as the universe gets bigger. This interpretation, dark energy as a cosmological constant, has been the default assumption of lambda CDM for over 2 decades, and if it is correct, it predicts a specific future for the universe: eternal expansion. An ever-growing cosmos where galaxies drift farther and farther apart, where stars gradually burn out, where the temperature of the universe asymptotically approaches absolute zero, and where, in the extremely distant future, nothing remains but cold, dark, empty space. This is called the heat death of the universe, or the Big Freeze. It is the lonely, silent end of everything, and for a long time, most cosmologists accepted this as the most likely fate of the cosmos, not because they liked it, but because the data supported it. Until now, in March of 2025, the Dark Energy Spectroscopic Instrument, known as DESI, published results that shook the foundations of this consensus. DESI is a remarkable instrument. It is mounted on the Mile Telescope atop Kitt Peak in Arizona, and it is equipped with approximately 5,000 robotic fiber optic positioners, tiny robotic eyes that can each independently aim at a different galaxy. Night after night, these robotic eyes swivel back and forth, pointing at galaxy after galaxy, collecting their light through fiber optic cables and feeding it to a spectrograph that measures each galaxy's spectrum and determines its distance and velocity. Since May of 2021, DESI has been building the largest 3-dimensional map of the universe ever created. By measuring the positions and velocities of millions of galaxies, DESI reconstructs the history of cosmic expansion in extraordinary detail. The key technique DESI uses is called baryon acoustic oscillations, or BAO. In the first few 100,000 years after the Big Bang, the universe was a hot plasma of particles and radiation. Sound waves traveled through this plasma, creating alternating compressions and rarefactions, like sound waves in air. When the universe cooled enough for atoms to form, these sound waves were frozen in place, imprinted on the distribution of matter. The result is that today, galaxies are slightly more likely to be found at certain distances from each other, corresponding to the size of these frozen sound waves. The characteristic scale is about 500 million light-years. This scale acts as a cosmic ruler. By measuring it at different epochs, corresponding to different redshifts, you can track how the universe has expanded over time. And by tracking how the expansion rate has changed, you can infer the properties of whatever is driving the expansion, namely dark energy. In April of 2024, DESI published results from its first year of data, based on observations of about 6 million galaxies spanning the last 11 billion years of cosmic history. when the team combined their galaxy data with independent data from the cosmic microwave background and from supernova surveys. They found something startling. The data showed hints that dark energy might not be constant. It appeared to be weakening over the last several billion years. Its density was not behaving like a cosmological constant. The statistical significance was 3.9 sigma, substantial but short of the 5 sigma threshold for a confirmed discovery. The DESI team was careful in their language, describing the results as hints rather than evidence, and emphasizing the need for more data. Many in the community expected the signal to fade as more galaxies were observed. It did not fade. On March 19, 2025, at the Global Physics Summit in Anaheim, California, the DESI collaboration presented their results from 3 years of data. The galaxy sample had more than doubled, from 6 million to nearly 15 million galaxies. The three-dimensional map they had constructed spanned 32 billion light-years of space. It was the largest and most detailed galaxy map ever created. And the hints had become stronger. When combined with CMB and supernova data, the DESI 3-year results showed a tension with the cosmological constant model of 4.2 sigma. The odds of getting this result by chance, if the cosmological constant is correct, are about 1 in 30,000. That is like flipping a coin 15 times and getting heads every single time. Seshadri Nadathur, a cosmologist at the University of Portsmouth and a member of the DESI team, said, "We are much more certain than last year that this is definitely a thing." But DESI was not alone. At the same conference, a completely independent group, the Dark Energy Survey, or DES, presented their own analysis. DES had spent 5 years photographing 12% of the southern sky using a camera mounted on the Victor M. Blanco telescope in Chile. They had created the most extensive catalogue of supernovas to date, and had identified the same baryon acoustic oscillation patterns traced out by millions of galaxies. Their analysis, combined with CMB data, found a tension with the cosmological constant of 3.2 sigma, and this tension disappeared when they allowed dark energy to change over time. 2 independent experiments, using different telescopes, different techniques, different data sets, arriving at the same conclusion. Michael Troxell, a cosmologist at Duke University and a member of the DES team, said, "This paints a nice consistent picture." The picture they were painting was one where dark energy is not a cosmological constant. It is not the fixed, unchanging energy of the vacuum. It is something dynamic, something that has been evolving over the history of the universe. And based on the data, it appears to have been getting weaker over the last several billion years. Let me describe what the DESI data actually shows, because the details are important and somewhat puzzling. When you reconstruct the history of dark energy from the DESI observations, what you see is that dark energy appears to have gradually intensified over the first several billion years of the universe's history, and then, around 6 billion years ago, it started to weaken. The strengthening phase is concerning to theorists because it implies something called phantom dark energy, a form of dark energy with exotic properties that most physicists consider unphysical. An energy that strengthens over time without an obvious source violates many intuitions about how physics should work. However, there is a potential explanation for why the phantom phase might not be real. Dark energy's effect on the universe in its early years was relatively mild, because there was much less space back then, and therefore the total contribution of dark energy to the expansion dynamics was small. The signal from that early era is weak and potentially unreliable. It is possible that the apparent strengthening is a measurement artifact, a quirk of the data from an era when the signal-to-noise ratio was low. Kim Berghaus, a theoretical physicist at the California Institute of Technology, expressed cautious optimism, saying that if dark energy turns out to weaken consistently throughout time, she would be inclined to believe the DESI results are real. But, she added, if it does go into the phantom crossing, I would lean more toward a systematic error. But whether or not the phantom phase is real, the weakening phase, the decline in dark energy density over the last 6 billion years, is supported by both DESI and DES data. And this is what has the cosmology community buzzing. Because if dark energy is truly weakening, then the fate of the universe is no longer what we thought it was. The theoretical reactions have been polar. On one side, Qumran Vafa, a renowned physicist at Harvard University who specializes in string theory, finds the result entirely natural. In his work Building Theoretical Universes from String Theory, he says, "You cannot construct a universe where the energy of space maintains a positive value forever. Eventually, the energy must fall, either abruptly or slowly over time. String theory, he argues, kind of demands that dark energy change. The DESI data, with its evidence of a slow decline, aligns beautifully with many string theory models. For Vafa, this is not a crisis, it is a confirmation." On the other side, Raphael Bousso, a theoretical physicist at the University of California, Berkeley, is deeply skeptical. He argues that the vacuum must have some constant energy, based on the known behavior of quantum fields. It is not optional. If DESI is detecting something additional that acts like a gradually thinning repulsive fluid layered on top of the constant vacuum energy, then some new undiscovered field or particle must be responsible. Bousso finds this implausible at the current level of statistical significance. He used a vivid analogy: it walks like a duck. It quacks like a duck. Is it a unicorn in a duck suit? For 3 sigma, even 4, I am not going to lose any sleep. Despite the disagreement, both camps acknowledge that the results are tantalizing. If dark energy is truly evolving, the implications are enormous. Let me spell them out. First, the fundamental nature of the cosmos changes. If dark energy is not the cosmological constant, then it is not simply the energy of empty space. It must be something else. Physicists call the leading alternative quintessence a dynamic quantum field that permeates all of space and whose energy slowly dissipates over time, like a battery running down. Quintessence is named after the 5th element of classical Greek philosophy, and it would represent a completely new fundamental component of the universe, something not currently included in the standard model of particle physics or in lambda CDM. Second, and more viscerally, the ultimate fate of the universe changes. If dark energy is constant, the universe expands forever, heading toward the big freeze. But if dark energy is weakening, other scenarios become possible. If dark energy weakens to 0 and then reverses, becoming attractive rather than repulsive, then the expansion of the universe could eventually slow, stop, and reverse. Everything that has been flying apart for billions of years would begin falling back together. Galaxies would approach each other. The temperature of the universe would rise. And ultimately, all of space, all of time, all of matter would collapse into a singularity. This is called the Big Crunch, and it is essentially the Big Bang in reverse. Some physicists have speculated about what happens at the Big Crunch. Could it trigger another Big Bang? Could the universe be cyclic, expanding and collapsing and expanding again in an infinite series of cosmic heartbeats? The idea is called the cyclic universe model, and while it remains highly speculative, the DESI data showing weakening dark energy is at least consistent with it. Alternatively, if dark energy fluctuates, if it weakens for a while and then strengthens dramatically, the universe could face a far more violent end. In this scenario, the expansion accelerates without limit, eventually tearing apart galaxy clusters, then individual galaxies, then solar systems, then planets, then atoms, and finally the fabric of space-time itself. This is called the Big Rip, and it is the most catastrophic possible end to the universe. Some models predict it could occur in as few as 22 billion years. Mustafa Ishak Boushaki, a cosmologist at the University of Texas at Dallas and a DESI team member, summed up the significance. It challenges the fate of the universe. It is game-changing. And then he added, now a Pandora's box is open for theories. So where do we stand? As of right now in 2026, the evidence that dark energy is evolving is strong, but not yet conclusive. The DESI 3-year results show a 4.2 sigma departure from the cosmological constant. The DES results independently show 3.2 sigma. Both are substantial, but neither has reached the 5 sigma gold standard. More data is needed. DESI is continuing to observe. Its robotic eyes on Kitt Peak continue to stare out into the universe every clear night, collecting photons from galaxy after galaxy. Its final map, based on the complete dataset, will include approximately 50 million galaxies and is expected to be completed by late 2026 or early 2027. This final map will have enough statistical power to either confirm or refute the evolving dark energy hypothesis with definitive significance. Meanwhile, other experiments are coming online. The DES collaboration plans to publish additional results later this year based on the clustering of galaxies and matter over the history of the universe, which reflects the tug-of-war between gravity's pull and dark energy's push. The European Space Agency's Euclid telescope, launched in 2023, is specifically designed to map the geometry of the dark universe. And the Vera Rubin Observatory, under construction in Chile, will survey the entire southern sky every 3 nights, providing an unprecedented volume of data for studying the expansion history. Kim Berghaus, contemplating all of these converging data streams, said, "We are having all these tensions now under lambda CDM that are popping up. From that perspective, I do not think it is the end of the story." And she is right. It is not the end. It is the beginning. But the beginning of what? Let me now pull all of these threads together, because we have covered an enormous amount of ground, and I want you to see how all of these apparently separate discoveries connect into a single, coherent, terrifying picture. James Webb has found impossible galaxies in the early universe, galaxies too massive, too bright, and too structured for the standard model to easily explain. James Webb has found supermassive black holes that formed too quickly, too massively, and too abundantly, requiring new formation mechanisms that our models had not anticipated. James Webb has revealed the little red dots, a hidden population of black hole stars wrapped in dense gas cocoons, objects that no one had predicted and that reveal the cosmic dawn as a far more violent and black hole-dominated era than any textbook described. James Webb has sharpened the Hubble tension to a crisis, with multiple independent measurement methods converging on an expansion rate significantly higher than the standard model predicts. And simultaneously, the DESI experiment has produced strong evidence that dark energy, the fundamental force driving the expansion of the universe, is not constant but evolving, weakening over time. These are not separate problems. They are all symptoms of the same underlying condition, the lambda CDM model, the standard model of cosmology that has reigned supreme for 30 years. Is showing cracks. It is not necessarily broken. Many scientists emphasize that the model still correctly predicts an enormous range of observational data, and that the anomalies may be explainable with relatively modest adjustments. But others believe the cracks are deep enough that a more radical revision is needed, possibly a new paradigm entirely. The honest assessment, the assessment shared by most working cosmologists, is that we are in a period of extraordinary uncertainty. The data is coming in faster than the theories can accommodate it. Every new observation from James Webb, every new galaxy map from DESI, every new measurement of the Hubble constant adds another data point that the current model struggles to fit. We are in that exhilarating, terrifying moment in science where the old framework is creaking under the weight of new evidence, but the new framework has not yet crystallized. This has happened before in the history of physics, and every time it has happened, it has led to a revolution. In the late 19th century, physicists could not explain why the spectrum of light emitted by a hot object did not match theoretical predictions. The theory predicted that the intensity of emitted light should increase without limit at shorter wavelengths, a catastrophe that was called the ultraviolet catastrophe. The resolution came from Max Planck, who proposed that energy is quantized, that it comes in discrete packets rather than continuous waves. This insight gave birth to quantum mechanics, one of the 2 pillars of modern physics. In the early 20th century, astronomers noticed that the orbit of Mercury did not precisely match the predictions of Newton's law of gravitation. The discrepancy was tiny, a slow precession of Mercury's orbit by about 43 arc-seconds per century that Newtonian gravity could not explain. The resolution came from Einstein, whose general theory of relativity provided a new, more accurate description of gravity that naturally predicted the observed precession. Newton was not wrong. Exactly, he was incomplete. His theory was a brilliant approximation that worked perfectly for everyday situations, but broke down under extreme conditions.